In this video, I'm going to go through review 1, our review of transformations both on the coordinate plane and without a grid. So for number 1, if the triangle shown below is mapped using the rule x, y goes to x plus 5, negative y, draw the triangle's image on the grid. So what I'm going to do is I'm going to start just by figuring out what those points are. So if I count the boxes, one of those points is 2, 1. Another one is 6, 1, and the other is 1, 8. So I'm going to look at this rule, and it's telling me to take each of my x values and add 5 to it. So negative 2 plus 5 is 3. And to change the sign of my y value. So if I start with a positive 1 for a y, that's going to change to a negative 1. Same thing for my second point. I'm going to add 5 to my x coordinate to get 11, and negate that y value. And once again, when I add 5 to 1, I get 6. And when I negate that y, it's negative 8. So I'm going to take a second just to plot those points. So I've plotted the triangle. Are the two triangles congruent and justify? Well, if I could find some sequence of rigid motions that would take my first triangle and map it onto my image, then I would be able to prove that they are congruent. So it looks to me like if I translate it, and then I reflect it over the x-axis, the triangles would land right on top of each other. And that's what's happening in my rule here. If I'm adding 5 to my x values, I'm translating right 5 units. And if I'm negating my y values, I'm flipping it over the x-axis. So are the two triangles congruent? Yes, because the triangle was translated and reflected. And the whole idea here is that you need to remember that both of these are rigid motions, so they're going to preserve two things. Distance, so the side lengths, and the angle measure for all of the angles in these triangles. So both of these are definitely congruent because there exists a series of rigid motions which maps one onto the other. For number 2, triangle ABC is shown below with the vertices at A, 3, -2, B, 3, -6, and C, 9, -2. Draw triangle A', B', C', the image of triangle ABC, after a 90-degree counterclockwise rotation about the origin. So remember, we have a rule for 90 degrees that's going to change all of our points to negative y, x. So if you're trying to visualize this triangle should be somewhere over here because I'm rotating 90 degrees and this is the counterclockwise direction. So again, if I'm rotating and I have a rule to apply, I could turn my paper 90 degrees, but just to make sure, I'm going to apply that bump switch rule that we've been talking about in class. So to find A', I'm going to bump the 2 to the front, but I'm negating the y. So that doesn't mean to make it negative, that just means to change the sign. So if I already have a -2, that's going to be +2. And the x is just going to bump to the back. So B' is going to be, if I negate that -6, it becomes +6, 3, and C' is going to be +2, 9. So I'm going to take a second to plot this. So that's what my rotation of 90 degrees would look like, and that looks pretty good to me because I assumed it would be in that quadrant to start with. So for part B, they're telling me that I have a new image, A', B', C', using a translation that results in these 3 points. And it wants to know what the rule for this translation was. So again, I'm going to take a second to plot those double primes just to see what it looks like. Right, so there's my triangle that's been translated. So I took the purple triangle to the red triangle through a translation. I went left some amount and I went down some amount. So they're asking me for a rule for this translation. So I did something to the x values and I did something to the y values. And it's just a matter of counting the boxes to see how far I went. Now, each of these points should have been translated in equal distance, so you can pick any of them to count the distance between. So I'm going to pick the distance between C' and C'. So I can go left 1, 2, 3, 4, 5 units. So I'm subtracting 5 from all my x values because I moved left. And I went 1, 2, 3, 4, 5, 6, 7 units down. So I subtracted 7 from all of my y values. So this would be the transformation rule. I take any point given x, y, and I take away 5 from the x's, and I take away 7 from the y's. You could also mention this as a translation that moves our figure left 5 units and down 7. both of those would be acceptable to view this transformation here. For number 3, in quadrilateral ABCD shown below, AD is congruent to BD, and angle ADB, right there, is 30 degrees. BC is perpendicular to both AB and DC. So remember that perpendicular lines create right angles. So if BC is perpendicular to both of the sides it touches, that means that this is going to be a right angle right here, and this is going to be a right angle right there. I don't know if that helps me yet, but I'm going to continue reading the problem. Given this information, determine the measure of angle DBC. So that little sliver right in there. So it almost looks like I don't have enough information here, but you got to think about, why did they tell us that two sides of that triangle ADB were congruent? Well, remember, if I have two congruent sides of a triangle, that's the definition of an isosceles triangle. And I know that if two sides are congruent, the angles opposite those sides are also congruent. So I know that something like angle A and angle ABD should be congruent. So they're just some value. I could set up an equation here if I really wanted to. 30 plus 2x equals the total sum of all the angles in my triangle, and that's 180 for every single triangle we work with. Or I could just try to reason this out. All of my angles should add up to 180, and I already have 30 degrees accounted for. So that means my other two angles should sum to 150 degrees. But if they should be equal, I can just take half of that to find that both of those base angles should be 75 degrees on their own. So angle A is 75, and angle ABD is also 75. Now just take a look at this picture we have here. I'm going to separate it so it's a little bit easier to see. ABD is 75 degrees. I don't know what the little piece is, but because BC is perpendicular to AB, both of these angles together should add up to 90. Right? This is like the complementary angles that we worked with last unit. So I could either set up an equation here, or I could just reason it out and say that if I subtract 75 from 90, my missing angle should be 15 degrees. And you could always check that just by re-adding them. So the measure of angle DBC is 15 degrees. Number 4. In the following diagram, triangle ABC has been transformed into triangle A double prime, B double prime, C double prime by the use of a sequence of transformations. Give one such sequence of transformations that would map one triangle onto the other. So I'm going from this pre-image to this image. The first thing I always like to start with, if the triangles aren't close enough together, is a translation. So I'm going to translate, if I'm counting my boxes, 1, 2, 3, 4, 5, 6, 7 left. So I'm going to start with translating 7 left. And just so they're connected, I'm going to move it down 1 as well. So if I do that to all of my points, my B prime would land right there, my C prime would land right there, and it looks like my A prime would land right there. So these triangles are almost mapped onto each other, but it looks like I still need to do a reflection. The problem is, if I want to say I'm going to reflect, I need to state what line I'm reflecting over. So it's going to be this side that's made by B double prime, C double prime, and that's just a horizontal line right there. Remember that all horizontal lines are of the form y equals whatever that y value is, and that's 1, 2, 3, down 4. So I'm going to reflect over y equals -4 to get those two triangles to map onto each other. And the whole idea here is that this is how we could prove that the two triangles are congruent, because these are both rigid motions, a reflection and a translation, and I know that rigid motions preserve side length and angle measure. That's going to be my justification for why these two triangles are congruent. So all I did was move them and then reflect, so it doesn't change the size or the shape. Number 5. In the diagram shown, AE and BD bisect each other at C. So BC is the same as CD. Give a rigid motion that would map triangle ABC onto triangle EDF. So just one thing to note is that if this is the order of the letters they're giving me, A should map onto E, B should map onto D, and C should map onto C. So I'm going from ABD, so I'm starting there, and I want to get to that triangle. It looks to me like if I fix C in place and just spin it around until A coincides with E, those triangles will land on top of each other. So the way I'm going to word this is I'm going to rotate triangle ABC. It looks like it could be 180 degrees, but I'm not 100% sure. So I'm just going to say rotate about point C until A maps to E. So it's going to come all the way around. A is going to map to E, and also B is going to map to D, exactly where I need them to be. So that's the transformation that gets me there. And again, why would that show that these two triangles are congruent? Because rotations are rigid motion, and we know that they preserve side length and angle measure. Number 6. Given a regular pentagon, remember that just means that all the sides are the same and all the angles are the same, shown below with center F, answer the following questions. What is the minimum angle needed to map B onto E using a counterclockwise rotation about F? So I want to get B to map onto E. Remember to find the minimum rotation needed to map a figure onto itself. As long as it's a regular polygon, you could take one full rotation and divide it by the number of sides, or the number of angles, because that should be the same, in your polygon. So in this case, I know 72 degrees counterclockwise would map this figure right on top of itself. So what that looks like is if I have this pentagon right here, and I turn it 72 degrees, let's see if I can get this, it would land right on top of itself. All right, let's see if we can get 72. Perfect. Right, so that's the idea. But that would only take B over to A. And I want to get B to E. So I'm thinking to myself, it wouldn't have to be just one 72 degree rotation. It would have to be two 70 degree rotations to get B to land on top of E. So that's 144 degrees. If I wanted to get to D, I would just go another 72 degrees, and so on and so forth. So the question is, why isn't 180 degrees a rotational symmetry for this figure? So if I turn it all the way upside down 180 degrees, notice that the figure doesn't map onto itself. All right, I'll get as close as I can there. But you get the idea. None of my vertices are matching on to the original vertices of my polygon. The whole reason that happens is because 180 is not a multiple of 72. I know that only multiples of 72 are going to map this figure onto itself. The other question is, how many lines of symmetry does this pentagon have? So a line of symmetry is a line such that if I sketch it in my picture, and I reflect my figure over that line, it would land right on top of itself. So for this line, A would map to B, or E would map to B, and C would map to D. So that's definitely one, but I could always turn my paper and do that from each vertex. All right, so I'm just going to sketch these in. That one, that one, that one, and that one. Of course, you'd use a straight edge. Those would all look a little bit nicer. But the idea is I could take any of those lines and reflect over it, and it should map perfectly onto itself. So in this case, there are 5 lines of symmetry. Which regular polygon has a minimum rotation of 45 degrees to carry the polygon onto itself? So you've got to think about, that's some portion of my full rotation of 360 degrees. If I divide 360 by 45, I find that there are 8 groups of 45 within 360. So if I rotate 45 degrees 8 times, that's a full rotation. So what that's telling me is that there are going to be 8 times where my figure coincides with itself. So as I'm looking at my answer choices here, remember an octagon has 8 sides, a decagon has 10, hexagon has 6, and pentagon has 5. My octagon would be the one with the 8 sides here. If you're not quite sure, remember we could take 360 and divide it by the number of sides, and that's going to tell me the minimum rotation to get a polygon to map onto itself. So octagon here would be the best fit. If they told me it was something like 36 degrees, then I would be looking at a decagon, and so on and so forth. So for something like number 8, I'm given a regular hexagon, that means that there are 6 sides, is rotated around its center counterclockwise, determine and state the minimum number of degrees in a rotation such that the hexagon will coincide with itself. That just means it's going to land on top of itself. If you could tell me that there are 6 sides, all you need to do is take 360 degrees, divide it by 6, because there should be 6 instances where these vertices map on top of each other. Number 9. Given right triangles ABC and DEF, where angle C and angle F are right angles, all that other information, they're telling me that these sides are the same and that this is congruent to this, which describe a sequence of rigid motions that would map ABC onto DEF. Notice that none of my vertices are touching. I need B to be on E, I need C to be on F, and so on. So the first thing I'm going to do if my triangles aren't touching is start with a translation. So I'm going to translate, and it doesn't tell me which way to go, so I'm just going to translate triangle ABC such that C maps to F. So I'm going to take this triangle right here. Remember, translating is just sliding. So I'm going to take this triangle and I'm just going to slide it this way such that, my C prime would be over there, my B prime would be over there, and my A prime would be up there. Now it looks like I'm almost good because these are symmetric, and if I reflect over DF, I'd be done. So I can now reflect that triangle, and if you're reflecting, give me a line you're reflecting over, DF. So that would take that blue triangle and map it onto the red triangle right there. So my triangles were close together, so I only needed 2 different transformations there. But for something like number 10, it might be a little bit more difficult. I need to describe a sequence of rigid motions that would map ABC onto DEF. So I need to go from here to here. It looks like there was a rotation, maybe there's a reflection of some sort, but it's too hard for me to describe right now. So what I'm going to start with, just so that I can make it easier to describe what's happening here, is I'm going to translate my triangle ABC such that one of my vertices matches up with where I need it to end up. So I'm going to start by translating triangle ABC to map C to F. Now, if you can't visualize where C is going to go, remember the order of the letters matters, right? So C is going to map to F, A is going to map to D, and so on. So now I've got like an A prime here and a B prime here. Now, I know that CB should match up with FE just based off of the order of the letters that I see. So if I rotate it, I want C prime to stay in place. So I'm going to rotate about point F. But I don't really know how many degrees it is. It looks like it's a little bit less than 90, but I don't have my protractor, so I can't measure it. So I'm just going to say rotate about point F until B prime maps onto E. So if I were to do that, I'm closing these figures onto one another so that my picture would now look something like that, where that's my A double prime, and they're latched onto one another. So my last step here, once they're connected, is I can again reflect. And I'm going to reflect over EF. And the whole reason that works is that 2 of my points are already where they need to go. This is where C double prime is, that's where B double prime is, they didn't move. I know B should map to E and C should map to F. The only thing I need to do is get A to map to D. So this would be the most I would ask of you, something that requires at most 3 transformations, get one figure to map onto the other. And I know that they're congruent, but if I didn't, this would be a way to prove that they're congruent. Number 11. In the diagram below of triangle ACD, segment DB is a median to AC, AB is congruent to DB, and the measure of angle DAB, right there, is 32 degrees. What is the measure of angle BDC right up there? And one hint I gave you is that you could figure out the triangle ABD over there and triangle BDC over here are isosceles. Let's break apart some of those givens. They tell us that DB is a median. And remember, a median is a segment in a triangle that goes from a vertex to the midpoint of the opposite side. So that would mean that point B there is a midpoint. of side AC. So segment AB is congruent to segment BC. But they also told us here that AB and DB are congruent. So all three of those segments are congruent. Now, if I just look at triangle ABD right over here, this triangle has two congruent sides. So I know that this is an isosceles triangle. And a property of isosceles triangles is that if there are two congruent sides, then the angles opposite those sides are also congruent. So there should be two congruent base angles there. So if BAD is 32 degrees there, I can make an argument that angle ADB is also 32 degrees. Now that helps me a little bit because I'm trying to get here, and I don't really know how I'm going to get there, but I'm going to fill in all the angles that I can. I noticed that in triangle ADB on this side, I have 2 out of my 3 angles. And if I want to find the third angle of a triangle, remember that all the angles in a triangle should sum to 180 degrees. So if I already have 32 degrees and 32 degrees, that's 64 together. And if I subtract that from 180, I find that really that obtuse angle right there should be 116 degrees. And that helps me fill in the angle on the other side of B for angle DBC. Because those are two angles that together add to a straight line. So those are supplementary angles that should also sum to 180 degrees. So if angle ABD is 116 degrees, it should be the case that angle DBC is 64 degrees. Because both those together sum to 180. Now, we're finished with triangle ABD. Let's just constrain our view to this triangle on the right, triangle BDC. I'll redraw it over here just so we have it. These two sides are congruent, and I know this vertex is 64 degrees. So this is also an isosceles triangle, and if there are two congruent sides, there should be two congruent base angles here. Well, I know that one of my angles is 64, and together all of these should still sum to 180. So my two base angles should sum to 116 degrees, so that all three angles sum to 180 degrees, but I know they should be equal to each other. So if I take that 116 degrees and divide by 2, I find that each of those base angles are 58 degrees. So it's like a puzzle. All we started out with, if I look at my original picture again, was this 32 degrees. But I said, well, if it's isosceles, this should also be 32. And if it's a triangle, all the angles should sum to 180. And if these two lie on a straight line together those two should sum to 180. And then this is also another isosceles triangle, so the base angles are congruent. So try to work with all of the geometry facts that you know about isosceles triangles, supplementary angles, and isosceles triangles specifically. So for angle BDC, that's going to be 58 degrees. Number 12. Segment CD is the perpendicular bisector of segment AB at E. I'm going to sketch a picture of this scenario. I've got one segment, AB, and CD is the perpendicular bisector. Well, if it's the bisector, it should cut right through the middle at the midpoint. So when it cuts through, AM and MB are going to be the same there. And if it's the perpendicular bisector, it should intersect my segment and form 90-degree angles. So it could look something like this, where that's segment C and that's segment D. So if I wanted to name one pair of congruent segments here, I could say that segment A, that should be E, because that's where I said they intersect. AE is congruent to EB. The reason that's true is because E is the midpoint of AB. And the reason I know that is because they tell me this is a bisector, and a bisector of a segment should pass straight through the midpoint. Now, it gets a little tougher if I want to name a pair of congruent angles. So I want to think about that perpendicular part. I know that perpendicular lines form right angles. So angle CEA should be a 90-degree angle. But I also know that there are 4 right angles that are created. They're all around point E. So it's also the case that angle CEB is 90 degrees. Or you can make an argument that angle AED on the other side is 90 degrees. Or that angle BED right there is also 90 degrees. So if I want to name one pair of congruent angles, I could pick any of these 2. So I'll say that angle CEA is congruent to angle AED, because I know all of those are right angles, and I know that all right angles are congruent. Number 13. Segment PS is an altitude of triangle PDQ. If the measure of angle PSD is 6x minus 6, the measure of angle PDQ is 3x minus 7, find the measure of angle PDQ. So really I need to figure out what x is and then substitute it in there. The first keyword that jumps out to me is altitude. Remember that an altitude of a triangle is a segment that goes from a vertex to the opposite side, but is perpendicular to the opposite side. So it doesn't necessarily need to go through the midpoint, but it always needs to make a right angle. If that's the case, I know that angle PSD should be a right angle, or 90 degrees. But it's also represented by 6x minus 6. So I can set 90 degrees equal to 6x minus 6 and solve from there. If I add 6 to both sides, I get that 96 is equal to 6x. And if I divide out the 6 on both sides, I find that x is equal to 16. That's a good start, but that's not exactly what I needed to finish this problem. I need to figure out what angle PDQ is. So I can take my value of x, and if I know that the measure of angle PDQ is represented by 3x minus 7, I can make a substitution for x and put in 16 there. So 3 times 16 is 48, minus 1 is going to be 41 degrees. So realistically, I could do a lot of things here, even though this is the answer I'm looking for. Now that I know this is 41 degrees, I know this is 90 degrees. If I wanted to figure out this angle on the other side, that should be 90 as well, because those 2 angles should be supplementary. Or if I wanted to figure out this third angle, if I'm looking at this triangle right here, I know that all 3 of those angles should sum to 180. So there's lots of things I could do here. Keep that in mind for something like number 13 and something like number 11, where you need to put your detective hat on and really think about what rules you know about angles.